If you have ever witnessed a procession or maybe just a road race, be it a marathon or a bicycle race, you may have wondered where are these people going? They seem to be going further and further on, but where exactly are they going? What is their goal? In a way, this is the question that we will be asking in the context of sequences. Of course, we're not going to be looking at people, so we're going to say goodbye to these guys wherever they're going. We're going instead to look at sequences from the mathematical point of view. And from that point of view, a sequence is just a function. It is special only in the way its domain is set up. In fact, a sequence is a function whose domain consists only of the natural numbers n equal 1, 2, 3, 4, 5, etc. That's why I wrote the function as a equal f of n. You're noticing a little bit of difference in the notation using different letters. That is just to emphasize the fact that we're dealing with sequences and not regular functions. But otherwise, the idea is still the same. Of course, the questions are going to be different, and we're going to be approaching them in a different way. But in terms of its essence, a sequence is just a function. So if we want to look at it from the graphical point of view, a function that of the kind that we've seen so far would look like this. It would have as domain some kind of interval or maybe even the whole set of real numbers, and its graph is going to be a continuous curve. For sequences instead, we're only going to look at what the function does at specific values, which generally is going to be those natural numbers 1, 2, 3, 4, 5, but it could also be having some variations on that. For instance, we could start at 0, as you can see in this situation. The point is that we're only looking at some domain which starts at a certain point, and formally we can always change it so that it starts at 1, but doesn't have to be, and then it goes on for successive natural numbers 1, 2, 3, 4, 5, etc., all the way to infinity. Okay? That means that what we're going to do is we're going to ignore anything that is in between, and therefore all we're going to be focusing on is the sequence of dots that represent the values of this function, as the input value starts at 1 or at 0 or somewhere else, and it keeps going towards infinity. Okay? Now, the natural numbers go on to infinity, and that's always an important thing. As I said, formally we always we should always make a sequence start at x equal 1 or n equal 1 in this case. But in fact, we can always adjust it a little bit and make it start somewhere else. However, what is not going to change is that we're going to consider this sequence all the way to infinity. And for that reason, people also talk about infinite sequences. However, just to be a little bit more efficient, we're going to just call them sequences, not infinite sequences. We're going to assume that they're always infinite. Okay? Now, again, in terms of notation and jargon, the image of a natural number in a sequence is called a term of the sequence, and later on, as we're moving to the next topic, you're going to understand why we call it a term, which is something we call the pieces of a sum in algebra. But we're going to call this a term of the sequence. Again, in terms of notation, we're going to say that a sub n, we're going to denote by a sub n the value of this sequence at the nth place. There are two ways to define or present a sequence. One is the one I've just told you. Okay, so one thing we can do is we can take just a regular function and restrict it to the natural numbers. So we can start from any good old function y equals f of x, as long as it is defined for all natural numbers, and then start from it, construct a sequence which is just an being equal to that same function evaluated at n. Okay. But there is another way of doing it, which sometimes it can be more interesting, although it is usually a little bit more difficult to handle. We're going to see some examples of that. And that's to define the sequence recursively. What does that mean? It means that we're going to start by telling what the first element of the sequence is, what's f of 1. Sometimes we may have to define also f of 2, f of 3, but the first few, a finite number of values at the beginning, and then we're going to define the remaining ones in terms of the previous ones. So in this sort of introductory definition here, we define the first one, and then the second one will be some function not of n, but of the previous number. And then the next one still is going to be a function of the previous number, and so on and so on. The most famous example of a recursive sequence is the Fibonacci sequence, which most likely you have seen before. And so just as a reminder, how do we define this sequence? This sequence is not defined by letting us know what is the term in position n, but by telling us first of all what is the beginning number. And for convenience, we're going to start with a0. So this is one of those strange sequences where we start at 0. Again, we could shift everything by one position and make it start at 1 if we wanted to, but for convenience we're going to start at 0. And we're going to say the 0th element is 0. The element a1 is going to be equal to 1, and then from here on we're going to define the next element as the sum of the previous two. So once we have that a0 is equal to 0 and a1 is equal to 1, a2 is going to be equal to the sum of 0 and 1, which gives us again a 1. And then the next one is going to be equal to the sum of the previous two, which is 1 and 1, so it makes us 2, and so on and so on. Let me show you what that sequence looks like. Once again, I'm sure you have seen it before, but this is what the sequence looks like. So let's analyze it for a second. So in order to find the third number, so this number here, the number 1, how is it obtained? Well, that's the sum of the previous two numbers, so the sum of these two. The next number is going to be equal to 2, and that is going to be equal to the sum of the previous two, so it's 1 plus 1. The next one still is going to be this number here, 3, and that's again the sum of the previous two numbers, 1 and 2. And so on. The next one is 5, which is the sum of 2 and 3, etc., etc. So you can see that we can keep going with this sequence all the way to infinity, and again defines a sequence of numbers, but it's not defined as f of n, is defined always in terms of some previous numbers.